Hello everyone. I just finished working on documentation for a code that I've been working on for about maybe 6 or 9 months now. And while it was fresh on mind, I thought to walk through the basics of how to put together a Python package, how to automatically test it, and then deploy documentation onto a tool like GitHub Pages. As you can see here, XML has a website you can go to, xlearn.github.io/xml, that links you to all of the documentation for it, including both kind of tutorials that are written by hand and API documentation that's automatically populated. And all of this documentation is created every time I push changes to the code. Additionally, whenever I make changes to the code, I get automatic tests that let me ensure that everything is working properly and I can know when it isn't. So let's walk through the basics on how this is done, starting off with how we create a Python package that can be installed relatively quickly. So let's switch over to some code for that. The core for setting up a Python module is twofold. A Python module itself is just a directory structure that contains files that have a .py extension to them. More specifically, you need files that contain a .py and one file that marks it as a module, something that typically has that must have the name 2 underscores in it, 2 more underscores. And this is the kind of thing that all Python projects have. This isn't just specific to ones you write. So let's take a look at NumPy. NumPy in itself is actually a file named numpy.init. So this is the mechanism that Python uses for everything. The other combination of tools besides having a directory structure is some information telling Python which directory and structure to look for, and some additional metadata about it, such that if you were to eventually say publish this onto PyPy, it can be easily found by others. And that information is stored in the pyproject.toml file. Pyproject.toml is relatively new. It came around, I think, a few years ago when Poetry, another Python packaging technology, came out, and it replaces the setup.py and requirements.txt files that you may have seen, along with some other Python approaches, with a single file that's written in a markup language called TOML. I'll send you the template for this and the documentation from Python's packaging tutorials that explain the nuances of what's defined in here. But the key parts are a name and version of the package, as well as some descriptive details about what that package is and who made it. Then you have lists of dependencies for the Python module. And you can see here, I define typically a minimum version for any of the core dependencies of the library. For example, I rely on using ASC greater than 3.22. It's very important to at least mention a major and a minor version when you're listing a Python dependency. There are cases where there are things like TQDM that I know are not going to change in the foreseeable future. For those, I won't list a version, but for anything else that I know has an interface that may change and that I'm very tied to, like ASC, I'll put a major version at least, often a minor, to make sure that I get a good version installed every time I build the package. The rest of the markup captures things like where to find the Python module which you want to install. This is often inferred automatically for you, but I tend to just mark it out explicitly in case I have some utility scripts. Often my codes come with directories that may contain some other Python files, so I ensure that there's no ambiguity about which ones belong to my module and which don't. The rest of this are kind of more specific things. I put optional dependencies such that if you're installing, say, the module and you know you're going to want to test it later, you can install those dependencies later using a command that looks a little bit like this. Pip install, well actually, this is what I get for doing this in one take, where I can call pip install -e to put it in development mode, -dot to read from whatever is in the current library, and then the list of my optional modules, so .test. So as we'll see, when GitHub Actions builds my project and tests it, it will get those optional dependencies that, again, I've listed in my pyproject.toml file. So to wrap up what building the module looks like, I have a directory with files with .py extensions that contains subdirectories, also with files with .py, both of which containing this init.py file. So that's all you need to build a Python package. Another thing that I do, because a lot of my projects involve deploying onto computing systems with very different hardware on them, is I'll create a Anaconda file that tells me how to install the dependencies specific to the hardware that I'm using. For example, in XML, I use TensorFlow. When I test this locally, I'm not bothering to run anything on the GPU, so I'm installing the TensorFlow.-CPU version. There are other projects. XML is still early enough a code that I don't have an environment file built for other supercomputers. Well, built for supercomputers. My desktop computer is not one. I'll create a version that say has a version of TensorFlow that's specific to the CUDA libraries that are available on that specific supercomputer. But I don't have an example for them now. What this will allow me to do later is give you installation instructions that can tell you to install from a specific YAML file using Anaconda for a specific supercomputer. So that's the basics. Again, to create a package that's easy to install, write that pyproject.toml file, have it point to a directory of .py files, and create a anaconda.yaml file that will allow you to build that environment with the correct version of Python, with linked to the correct version of libraries that are installed on your system, such that you don't have to worry about having different installation paths, or that you can easily create those different installation pathways for different computing systems. So with that said, let's transition from going from having a Python module that you can install to one that you can trust reliably. And the key behind that is creating what's called a continuous integration script. For my point, I use GitHub Actions because it's well integrated with GitHub already. What this looks like when you're finished is a workflow that executes every time you update your software. What happens for projects, and what I'll show you for yours, is it will take one of those YAML files that you've created defining how to build your project, and it will build it. Here I have it build from my CPU environment because the GitHub Actions doesn't need to test anything with GPUs. It will do that. It will install any of those optional dependencies that I use for testing. Here is that pip install with an optional module that I told you about. It will ensure that my code is formatted cleanly. So what Flake is it'll tell me if I've got like indentation errors, or that I import a library that I don't actually need, and those other code style considerations that in the case of unnecessarily importing libraries could have code accuracy or performance implications, and others like indentation errors that when fixed just make your code easier to read. So after doing let, I might install some other libraries. This package uses CP2K, so I will install CP2K in my test environment. And at that point, I'm ready to run all of these unit tests. So unit tests cover specific functionalities of my code narrowly so that I can trace different problems down to specific parts of the library. For this, I use PyTest, which allows me to run a simple command line argument, in this case PyTest. I run it with coverage. We'll talk about coverage in a minute. I run them all in different Python interpreters, and I do some work to ensure that they don't take too long. And what this will do is it will go over a bunch of tests that I've already written and ensure that after I've changed the code, everything still works the way that I expect it to. So that happens on GitHub. I can also run it locally. Let's open up a terminal just to show you what that looks like. So here I'm going to run all my tests locally. It's going to find a bunch of files that are named test. It's going to find functions in there that start with the word test, and it will run them. I won't go through the complete details of how to write PyTest functions that are kind of efficient and easy, but let's show you just a few of them to give you an idea. Let's show here I'm testing functions around building machine learning models. So for example, I have one where I recreate the fingerprints used by my colleague to describe a molecule. So I will ensure that I can run that function with the input of methane, C. I can make sure that I can run it on a separate process and that the two give me the same values. So that's what a test looks like. I have about 60 of these for the XML project, each testing different functionalities, and they run every single time that I run GitHub, or that I push changes to GitHub. So you can look at that back at, let's say, a pull request that I finished yesterday. I was creating functions that ensure that when I run a, say, Gaussian calculation, it not only puts every calculation in a different temporary directory, but it labels them with the name of the molecule that I'm executing. And you can see that when I ran that, it ran my tests, it ensured that my code formatting was okay, and ensured that all of those tests that I ran worked well. And once it completed with that, as I promised, it ensured that these tests covered all of my new code. So that's using a tool or a website called Coveralls that goes through and takes some information out of my tests and ensures that every bit of code that I created was updated. So here I created some new functions within ASC, and I can go through and ensure that my ASC wrapper had every line covered. So here, lines in green are ones that one of my tests resulted in getting executed. And you can see that in this particular file, I have 100% coverage. My tests run every single line of this file, and this gives me some confidence that my tests are covering all of the potential behavior of my program. This makes me a lot more confident that there's no hidden bugs in here. We're not going to talk about the details of testing. There's some testing philosophies that you should consider when building good tests, but here I'm showing you the basics of how to do it, and that this coverage is executed with my build file. So now that you've seen what this GitHub action does, let's talk about how I created it. The core behind this is a GitHub Actions YAML file that I basically copy and paste between all of my projects. You can see each of these steps that I have, ranging from setting up my environment, to installing those dependencies, to running Flake, to running my PyTest script. And it's the same for basically every project. I'll link you to GitHub's documentation to describe what the details of this are, but the short version is create one of these files, place it in a .github.workflows folder, and that will result in this being executed every time that you tell GitHub it should. So here, every time I make a change, I push changes to GitHub, or every time I make a pull request. So that's the basics of automatic testing. Create a GitHub Action script that installs your environment from one of those installation files you showed. Have it run tests that you've created as test.py files, test something.py files that contain functions that are ran, and run it with coverage such that you can then send those coverage details to coveralls, and coveralls can tell you if you've covered all your bases. Alright, so last point, let's talk about documentation. So I use a tool called Sphinx to build documentation. Sphinx is a project that's used pretty broadly across the Python ecosystem, and what it will look like when you create a Sphinx project following their documentation is a folder that contains a configuration file defining how to build your Sphinx project, and a lot of RST files that contain a description of what your documentation will look like. I will talk you through the kind of details of all of the syntax you're seeing here. Restructured text, or RST, has some nice syntax for, say, denoting which text is actually code and then rendering it accordingly. It can make table of contents for you. It can link to external websites. So what you'll do when writing the documentation for your project is create a bunch of these files, link them together using a table of contents, and ensuring that they have test headers. So that's the basics of creating a restructured text file. There's documentation I'll send you to explain, like, why do some of my headers have equal signs underneath them and some have minus signs. Those are to create different levels. This is all covered well by Sphinx tutorials. The kind of subtleties in order to make your project look good is you want a few different things as part of your Sphinx build that make it really shine. The first of which is a tool called Napoleon, which is going to render your documentation for you and read the documentation strings from them to create nicely formatted files. So in order to make that happen, the first ingredient is creating a series of restructured text files that contain information about where to render details about specific Python modules. So here I've got a file that's describing everything in my xml.score module, and I fill it with these commands that tell me, hey, in this part of the file, document the xml.score. Here, document the xml.score.base file. And what you'll see on mine in this completed documentation, let's go back to GitHub pages. You'll see in my API documentation, oh, here it has rendered all of my documentation. And one thing you'll notice in this documentation is that it describes the type inputs to functions and describes what the parameters are. Now the cool thing about Napoleon, which I started off this conversation about, is that the way that it finds this information about what these parameters are. Here, I write my documentation in the Google style, and what it has done is parsed the Google style description or documentation style descriptions, identified what that means, mapped them to the form that Sphinx will know how to render into these nicely formatted pages. So you'll note here I call parameters args within the Google style. Napoleon is smart enough to know how to reformat it such that you get a very consistent style of documentation for your project compared to what other people read. So that's the bits of it. I also have it linked because I tend to read source code if I don't understand someone's documentation. And you can see I've got these nice descriptions that link me to the between the source code and the documentation, and that is a result of a different line in my configuration file called view code. It provides those little documentations where you render it. There's also intersphinx, which does some handy things like, let's go to my quick start. If another project is subscribed using Sphinx, you can set it up such that you can link from your documentation to theirs. A lot of projects do this. All you have to do is point to where their documentation is with this intersphinx mapping, and that will set it up for you. So I link to Python, Mongo Engine Parcel, and Colmena, all of which use intersphinx. The last bit about kind of not just having a Sphinx project, but having one that looks nice is pick a theme. There's a website for all of the available Sphinx themes. They'll give you a gallery of them. Pick one that speaks to you. I tend to pick one that looks different from projects that I'm used to give my project a new and modern feel. If you go to each of these projects, I'll also often explain how to modify them to fit a style that you like. Let's see if I can find one. It doesn't look like I can find that description very easily. Oh yeah, here's the configuration for awesome theme. So you can make it in your own particular style. As an example, for Colmena, Colmena is Spanish for beehive, so I give their documentation a honey yellow color, just for my own amusement. And again, to make it look slightly different than other projects, so that there's like a visual and newness feel to it. So that's how you create the files. What happens under the hood, let's go back to my documentation. Once you finish creating this folder, you can call make.html. Sphinx will build your documentation for you. You'll note that it's created this build directory.html, which you can then open up in your browser of choice and see how your documents look on your local computer before committing them online. That brings me to the last point I wanted to talk about today, which is hosting them online. So I just showed you how to build it locally with a make command. That's basically all you do to run the documentation hosted online. So let's go back to my GitHub actions. So my GitHub actions, let's go back to XML, have one type of documentation called deploying my documents. So let's go here and take a look at what it looks like. What it does is it builds my documentation and then deploys it to GitHub pages. The way that that's done is a very similar kind of GitHub file to the one that we showed you earlier. And like what you might expect, recreates the workflow that I did on my local computer. I install the environment that I need for my project. Here, I'm not just installing all of the dependencies that I need to run the code. I'm just installing the software. Then the ones which I require to render the documentation. There's actually what I didn't show you, a file called docs.requirements, which installs Sphinx. It installs my theme, Furo, and installs one of the codes that I'll need to render the documentation properly. Once that's done, I call make HTML, and then I tell GitHub to archive the information which is held within docs.build.html, and it's going to call it pages docs or something like that. The next part of my build script is a template I grabbed straight from GitHub's documentation. What it does is it takes my artifact that I just uploaded and deploys it to GitHub pages. You can see it's got an action step that does all of those gory details for me. So if you created your own project, it would look exactly, this part would look exactly like this. In fact, this may even look exactly the same if you have your project configured the same way I have mine. So long as you can install it with pip, it has a file named docs/requirements. You can make it with Sphinx make.html. All of that will work for you. So what this will happen is every time I push a build to my local system, oops, I clicked the wrong one. Let's go to my actions, deploy docs. You can see when it ran locally, I installed my dependencies. Here's my pip install. It built them. You can see here it's the log from my building. It uploaded the artifact and then deployed it to GitHub pages, and now it'll even show you it's been deployed to GitHub, xlr.github.io/xml. So I've got my documentation hosted online. Everything here is kind of generic to projects. I'm probably going to copy and paste a lot of this functionality for the next code that I'm working on, and hopefully you can do the same for yours.